This lesson is going to teach you how to get concentrations at equilibrium if they give you K equilibrium. So if you're turning A into B, and let's say you started with 1 mole of A, how much B will you get in the end? You will be able to predict that. You will also be able to predict how much A you'll have left over unreacted. In this lesson, you will also be able to do a shortcut where you don't have to use the quadratic equation. Okay? The idea is this. Let's see that this is you, and you weigh, this is your hair, and you weigh 100 pounds. Okay? Let's say you take away one piece of hair, and you weighed yourself again. So one hair's missing. How much do you weigh now? Well, your hair would probably weigh 0.0001 grams. So, depending on how accurate your balance is, what's 100 minus 0.0001? Well, it's pretty much still 100 grams. Okay? So the same thing with a very low K equilibrium constant. That means if your K equilibrium is 10 to the negative 4 or smaller, 10 to the negative 4 is 0.0001 grams. If your reactant is A and only 1e negative 4 is reacting, you're going to end up with the same reactant. So that will help you from not using the quadratic equation. Let me demonstrate. So it says when ammonia dissolves in water, here's ammonia right here. It's dissolving in water. Remember, H2O is a liquid. You do not put that into the equilibrium expression. The following equilibrium is established. If the equilibrium constant is 1.8 e negative 5, that means it's very, very small. K equilibrium is equal to products over reactants. That means you will hardly make any products. Okay, that means the leftover reactant is going to be big. You're going to have like 100 grams minus very little used up. You're going to still have a lot of reactant left. Okay, makes ammonium ion and the hydroxide ion. Okay, so the K equilibrium here I will write on the side is 1.8 e negative 5. Okay, calculate the hydroxide ion concentration in the solution. If 0.10 mole of ammonia, so you have 0.100 moles of ammonia is dissolved in sufficient water to make 500 ml solution. So this is 500 mils or 0.500 liters. That will give you 0.1 divided by 0.5. I wrote it here, 0.1 divided by 0.5 is 0.2 molar. So I'm going to put that here to start my icebox. So I'm going to use a molarity for my icebox. Okay, so this will be initial. How much do you have in the beginning? How it changes, and then at equilibrium. How much do you have at equilibrium? Okay, so here's my icebox. So you have 0.2 molar, and you don't have to be concerned with the water because the concentration doesn't change, it's a liquid. It says calculate the hydroxide ion concentration. So they want the hydroxide ions right here. And that is when the reaction is done at equilibrium. So this is what they're looking for right here. Okay? So you have 0.2, and in the beginning it says you have only ammonia is in there in the beginning. So this is 0, and this is also 0. So you're going to do minus x. There's a 1 there, so that's a 1x. You don't need that in the equilibrium expression. You know what, I'm going to erase that because they look like x's. Don't need to be concerned with that. And then this is going to be, there's a 1 there, so plus x and plus x. So what you're interested in here is 0.2 minus x is what's left over, and this is going to be x and x. Okay, so the K equilibrium expression would be ammonium times, I'm sorry, the plus is inside, times OH minus divided by this products over reactants, which is NH3. And again, you don't write the water because it's a liquid. So now we plug in the numbers. We have 1.8 e negative 5 here equals the concentration of ammonium at equilibrium is x. Concentration of hydroxide is x also, so x times x is x squared, because this is x and this is x also, divided by 0.2 minus x. So you can see that I am about to use the quadratic equation to solve for x, but the shortcut is this. Noticing that the amount, this number right here that you're using, is very, very small. You're going to have a very small x right here because the equilibrium constant is very small, which means you will make very little product and you will use very little reactant, which means that this reactant that you're using is negligible or very, very little. It's the same analogy as you weigh yourself, you're 100 pounds minus the hair, which is very small, you're still 100 pounds. It starts at 0.2 molar ammonium minus something very, very small. It's still going to be 0.2 in the end. Therefore, in this equation, this minus x can be negligible to 0. So now your equation is very simple. You do not have to use the quadratic equation. So x is going to be equal to 0.0019, which is the molarity of ammonium hydroxide. So it's 0.0019 molar ammonium, and also 0.0019 molar of hydroxide. And if you want to see how much ammonia is left over, you're going to do 0.2 minus 0.0019 is pretty much still 0.2. Do you see that? Molar of ammonia. And these are the equilibrium concentrations. That means this is what you have in the beaker when the reaction is done. Okay, so you're wondering, Mrs. Lozano, how do I know if it's small enough that I can just take that away? You know when the first thing you look at is Kc is less than 10 to the negative 4. Okay, or if the percent ionization is less than 5%. Okay, so for example, do you see this x right here? This x should not be more than 5% of the original. That means your hair should not be more than 5% of your total mass. Okay, if it's more, then it's no longer negligible. So what you can do is you can check the percent ionization is equal to 0.0019 molar of the original compared to how much you had in the original. 0.2, that's how much reacted, times 100. Okay, and that is, let me calculate that, 0.0019 divided by 2 times 100. 0.0019 divided by 2 times 100 is 0.09. Not even 1%. 0.095 of a percent. Okay, so if your percent ionization is less than 5%, percent ionization or percent reaction, percent that reacted, okay? In this case, this ionized, okay? If it's less than 5%, then you may take away the x and call it negligible and solve for x that way. So you do not have to use the quadratic equation.